Integration is probably one of the hardest things to do in calculus. It's super messy, the algebra is complicated, you need a lot of different technique, and it's exhausting. But today, it's not gonna be the case. I'm gonna show you that in the complex plane, it's actually really easy to compute integral thanks to the Cauchy formula. So let's jump right into it. Here is the magic trick. Cauchy Integral Formula says that if you have an holomorphic function f of z on a closed loop gamma, then the integral of f of z divided by z minus z0 around that loop is simply equal to 2 pi I multiplied by the value of the function at z0, and that's it. Let's look at an example. Consider the integral of z squared plus 1 over z around the unit circle, oriented counterclockwise. The singularity, our problematic point, is only z equal to 0, and our function, z squared plus 1, which is in the numerator, is analytic. So to evaluate the integral, what we have to do? Well, we get 2 pi I times the value of the function at 0, which in this case is just 1, and that's it. Our integral is only 2 pi I. Let's see how it works in some exercises. As a first exercise, we are going to do the integral along the unit circle, and we are going to always orient it counterclockwise of e to the z over z. So usually you should do, I don't know, a couple of steps at least of integration by parts to solve this problem. But here, with Cauchy integrals, it's super easy. So let's see. First, I'm gonna draw the unit circle, which is our contour of integration. Okay? I'm gonna draw it slightly bigger. Okay? So this is the unit circle. Now, where this function has singularity? Well, the only problem is where z is the denominator. So when z is equal to 0, I have a singularity. So upon the singularity, exactly z equal to 0. Okay, but now let's look at Cauchy's formula. Cauchy formula tells us that the integral along a contour, a closed loop, of an analytic function f of s over s minus z ds, so s is my variable integration, is equal to 2 pi I f of z. So what does it mean? It means that if I have an holomorphic function, so it's analytic, like I have it here, e to the z, divided by s minus z, so I have a function with a singularity at z here, then this integral along this closed loop is equal to 2 pi I, the function evaluated at the singularity. Well, we can apply it here, and immediately we get that this integral is equal to 2 pi I. Now, f of z for me is going to be e to the z evaluated at 0. And e to the 0 is equal to 1, so times 1, so this is just 2 pi I. Now, let's level up a little bit. So, we are integrating in z to the power 3 over z minus I times z squared minus 4 over the circle centered at I of radius 1. Okay, so this is the circle of radius 1 centered at I. Okay, as before, what we do, we draw our contour. So this is gonna be I, and I have my contour is here. It touches the real axis. Okay, and now what do we have to do? Well, as before, let's try to identify where my function, the integrand, has singularity. So the first singularity is when z is equal to I, so exactly in the center of the circle. This is the first singularity. And then the second singularity is when z squared minus 4 is equal to 0, which means that z is equal to 2 or minus 2. So 2 is going to be something like here, probably, and negative 2 is going to be here. It's not in scale, of course, but kinda. Okay, and now how can we compute this integral? Well, Cauchy formula tells us that the singularity has to be inside our contour of integration, okay? So here, the singularity of 2 and negative 2, they do not really matter, okay? Because the function does not have any problem there. So, let's rewrite it down our Cauchy formula first. So, the integral over a loop of f of z over z minus z0 dz is equal to 2 pi I f of z0. Okay, this means now that I have the singularity at z0, and f of z has to be analytic, there, inside my loop omega, gamma, sorry. In our case, the function z cubed over z squared minus 4 is analytic inside the domain, because it does not have any singularity. So this one can be our function f of z. And z minus I is our z minus z0, which means that my integral is just equal to 2 pi I, don't forget about the 2 pi I, times the function evaluated at I, which is I to the power 3, divided by z squared minus 4, so z squared is I, so minus 1, minus 4. And this is equal to negative, so plus 2 over 5 2 pi I times I, so negative, negative, positive, so this is negative 2, sorry, too many 2's here, 2 over 5 pi. And that's it. So this trick works when the denominator is of the form z minus z0. But what if the denominator is squared or cubed? Standard Cauchy formula does not apply. But I'm here to tell you that actually computing this kind of integral with denominator is of higher power is equivalent to computing derivative of our holomorphic function f of z. In particular, the generalized version of the Cauchy formula tells us that the nth derivative of f evaluated at z0 is equal to n factorial divided by 2 pi I times the integral along a contour gamma that encloses the point z0 of f of z divided by z minus z0 to the power n plus 1. After isolating the integral, which is usually what we do to solve the exercise, we get that the integral along this closed loop of f of z divided by z minus z0 to the power n plus 1 is equal to 2 pi I over n factorial times the n derivative of f at z0. So let's see the power of this formula in action in a couple of exercises. So now let's try to apply the generalized Cauchy formula, okay? So we're going to integrate e to the 3z over z minus 1 minus I squared on the circle of radius square root of 2 centered at I plus 1, okay? So again, always the same things. Let's draw our contour of integration. Our contour of integration is somewhere here. So this 1 plus I is the center, and then I have to do my square root 2 circle, which looks something like this. And the only singularity of the function, again, is the center of this circle. Okay, so I'm exactly here in the center. And in this case, I'm always integrating counterclockwise. Okay, so the generalized Cauchy formula tells us that if I have a analytic function, f of z, and here I have an analytic function here, e to the 3z, divided by z minus z0 to the power n plus 1, and in this case I have z minus z0, power 2, so for me n is going to be equal to 1 in this case. Then this integral along this closed loop is equal to 2 pi I over n factorial times the nth derivative of my function evaluated at z0. So for me, this implies that my integral, it would be equal to 2 pi I divided by n factorial, for me n is equal to 1, so just 1, times the second derivative of my analytic function, e to the 3z, evaluated at my point. So in this case, the derivative of e to the 3z is 3 times e to the 3z, so it's e to the 3, 1 plus I. You can simplify this a little bit, this becomes 6 pi I times e to the 3 plus 3i. And that's it. Last exercise for today, again, generalized Cauchy formula, in this case. So now I'm integrating the cosine of z over z minus 1 to the power 3. On the contour, the circle of radius 2. Okay, so you know the drill now. As always, we draw our contour of integration. So it's equal to 2. It's equal to 2 is somewhat like here. I'm integrating in this side. And where are the singularity of the function? Well, the only point when I have singularity is when the denominator is equal to 0, which means that my singularity when z is equal to 1 and z equal to 1 is here. Okay, again, as before, we can use our generalized Cauchy formula, and we have our function, analytic function f of z, which in our case is the cosine of z in this domain, divided by z minus z0 to the power n plus 1. So for us in this case, n plus 1 is exactly equal to 2, is equal to 3, which means that n is equal to 2. So n is going to be equal to 2 for us. And z0 is going to be equal to 1, because it's the point of singularity. And that's it, basically. We can just apply the formula, more or less. So, which means this integral is going to be equal to 2 pi I, divided by, so n is equal to 2, 2 factorial is equal to 2, times the second derivative of the cosine. So when I differentiate the cosine, I get cosine, negative the sine, minus the sine derivative of negative the sine is minus the cosine of x, so minus the cosine of 1. So this is equal to negative pi I times the cosine of 1. And that's it. So we have seen that Cauchy's formula is amazing to compute integral in the complex plane, and it makes them really, really easy. And I'm gonna tell you, you can use the same idea to compute integral in the real axis actually, and that's what I'm gonna show you in the next video. So thanks you for watching, and I'll see you next time.